Hey everyone, can you guys confirm if you guys are hearing me? Okay, I want to welcome you to another exciting uh, lecture. And of course, today we actually going to continue from, where we stopped on Monday. Uh, on Monday, we started analysis of covariance that I also call design with covariates. And of course, I actually have an introduction and I walk you through examples and I differentiated between analysis of variance and analysis of covariance and situations where we can actually use any of the two models. We're going to continue from there today, only that most of the work today we actually be on, examples, I'm going to give you code that you're actually going to run in R, for you to have, if you're dealing with the analysis of covariance. Okay, so just like what I said, that is actually going to be the focus of today. Now, there's something I want you see what I'm projecting right now. This is just a table that actually differentiate between the regression analysis, analysis of variance, and the analysis of covariance. And of course, uh, whether you are talking about multiple regression, you're talking about ANOVA, you're talking about ANCOVA. Of course, the dependent variable has to be continuous in nature. In any of that, the dependent variable has to be continuous. But you know what? What actually distinguishes a particular model from the other is basically the nature of the independent variable. The independent variable that are also called predictor when I'm talking about, um, you know, uh, if I'm talking about multiple regression, of course, the independent variable has to be continuous. Though we got a situation in regression where we can also consider categorical predictor. I believe you've heard about dummy regression. We did something like that before. But let me tell you this, uh, for the analysis of variance, the independent variable that I also call predictor have to be categorical. That's a must, okay? Because the numbers of levels of the independent variable will be the numbers of groups, we represent the number of groups that we actually want to compare. And in the case of analysis of covariance, of course, analysis of covariance is looking at more than one factor, and you know if one of the factor is categorical, the other one has to be continuous, and which means the one that is continuous is the covariate that we talk about. Of course, the covariate, we could have one covariate, we could have more than one covariate. That actually depends on whether you have certain hidden factors that could affect the response. uh for those of you who like dogs, do you know that if you actually want to look at the effect of breeds of dogs on the weight of dogs, okay, uh, one of the potential variable that could have it effect on the weight could be age. Age can be taken as a covariate, can be taken as a the covariate I will talk about, because age, in addition to looking at the how the breeds of dogs, how it affects the weight, you also need to put into consideration the age of dogs. So which serve as the concomitant variable that I talk about. Okay. Give me 1 second. Can you guys confirm if you guys are still hearing me? Okay, just thanks for that. Now, that is that. And of course, uh, I told you on Monday that that analysis of covariance is a combination of multiple regression model and analysis of variance model. Now, take a look at what I'm projecting right now. This is a multiple regression model that we've done before. And now, this is analysis of variance model, and in particular, this is analysis of variance with interaction. Take a look at that. Okay. Now, when I combine this with the multiple regression model, I'm actually going to have an ANCOVA model, which is analysis of covariance model. You could look at that. I'm actually combining, I want to combine the ANOVA with regression. Take a look at that. Of course, this is an ANCOVA model, because an examiner can actually ask you to state an ANCOVA model. So what I just stated right now is an ANCOVA model. You know, this guy here is a continuation of this. Okay, it's a continuation. Okay, so it cannot contain that. That was why I put it right here. So it's just a single uh, straight line. Okay, now that's an ANCOVA model. Okay, now uh, if you want to actually investigate ANCOVA model, you actually need ANCOVA table. But you know what? Let me first show you how the ANOVA table is going to look like, and so that you'll be able to appreciate how the ANCOVA table is actually going to look like. Now, this is ANOVA. This is a multiple regression table. You know, the multiple regression. You remember when we're dealing with the regression table, there's something we call ANOVA for regression. Do you remember that we did before? We use ANOVA for regression when you are trying to test for, the significance of the overall parameters in a model. You remember we talked about having ANOVA for regression, where we have the source of variation, you know, where we have, the regression, the error and stuff like that. You remember that? And of course, so this is multiple regression model, and this is ANOVA model. Just look at the ANOVA table right now. In the ANOVA table, you remember we've done something like this before. This is a two-way ANOVA table with interaction. Take a look at that. I have the factor A, factor B, as well as interaction. You remember that I actually walk you through. So when we actually want to do, why am I showing you multiple regression model table? Why am I showing you the ANOVA table? Because the combination of the two will actually lead to an ANCOVA table. Now, take a look at that now. This is an ANCOVA table. In the ANCOVA table, this is the way it's actually going to look like. In the ANCOVA table, you're going to have, as part of the source of variation, so you're going to have the covariance. Take a look at that. Of course, this guy, this guy, this guy, these are what you have in the conventional two-way ANOVA. You remember that? The other time we were dealing with the two-way ANOVA, that's the conventional, that's what we have in the table. But what you added now is just this guy here, which is the covariance. That was what you had it. And you know what? Your which means the sum of square covariance is actually going to be the total variation explained by the covariance. Okay, don't forget initially when we're considering ANOVA and I mean two-way ANOVA, the sum of square A here is a variation explained by factor A. Sum of square B, variation explained by factor B. Sum of square AB, the variation explained by the interaction of the two factors. And of course, the sum of square error is the unexplained variation in the system, in the model. and of course, the SST total, that is the total sum of square, total variation. So which means what we are actually considering right now, what is new here is the sum of square covariance. Okay, that's what is new. And you know what? If the sum of square covariance uh, is if the p-value associated with that is significant, then it means we've done a great job by minimizing the error. What we actually want to minimize in any study, is to minimize our error. And how can you minimize our error? Of course, if you are considering analysis of variance model, and where you are looking at the effects of levels of categorical variable on the response, of course, if there exists a potential factor that is not of primary of interest that I call covariate, if there's a factor that have effects on the response you are talking about, okay, of course, if it has effect, of course, when the p-value associated with that will be significant, and of course, you will be succeeded in minimizing the error. So which means if you consider a covariate that is significant, it is not called covariate that are significant, but I'm talking about the one that are significant. Of course, we got a way to investigate that. And that is the reason why one of the assumption of the analysis of covariance is that, you know, uh, the the covariance should have, should be related to the response, and we got a way to investigate that. So the table that I'm giving you right now is what we call the ANOVA table. If examiner asks you to give an ANOVA table, this is exactly what you're going to give. There's a different, what leads to an ANOVA table is the ANOVA model. I'm going to show you now. This is an ANOVA model. There's a difference between an ANOVA model and the ANOVA table. Okay, so now you can see that now, and I told you the combination of the regression model and ANOVA model was one that gave us an ANOVA model. Okay, so if you understand that one now, then the next thing I want to talk about, I want to go into examples. I've given you so many examples on analysis of covariance on Monday, but I'm going to give you another example right now. Make sure you watch out in the midterm too. You can actually be given some questions and they ask you to identify, or maybe you have a study and they ask you to identify what kind of model can be used in a particular study. Are you going to use ANOVA, or is going to be ANCOVA, or stuff like that? Now take a look at this as another example that I'm trying to state here right now. So let's say you had a study which compared the salaries of male versus female college graduates. Okay. Now the variable being studied are gender and salary. You are looking at the effect of gender on salary. Of course, you may want to test this using analysis of variance, because there are levels, the predictor is categorical. And of course, you can also use dummy regression here. Okay. Now, the variable being studied, like I said, are gender and salary, and the primary survey questions are related to those two main topics. But you know what? It is not only gender that determines the salary, okay? If we're able to identify another potential factor, like the number of time you spend, the number of years you spend in the workplace, okay? So, and that was why I said, but since salary increase the longer someone has been in the workplace, the concomitant variable, whenever I say concomitant variable, that is the covariate that I'm talking about. The concomitant variable, time out of college, has the potential to skew our data if it is not accounted for. So which means when you are trying to look at the effects of uh, when you are trying to look at the effects of gender on salary, of course, you need to consider other potential factor. If there's another potential factor, like you know, the time out of college, if you don't, and if the time out of college has you know, relationship with the salary, then you got to consider that, and that's a concomitant variable. Because if you don't consider that, it could have a way to skew your data. You need to account for that. Okay. Now, this is number one example. This is another example. I gave uh, I gave an example similar to this on Monday when I was referring to a state in the United States that actually that I know for farming, agriculture. Okay. Now take it, which is the state of Iowa. Now take a look at this. In a study comparing the effect of soil composition on the growth of tomatoes over 20 different locations countrywide. Okay, 20 different locations. You want to consider, you're looking at the effect of composition on the growth of tomatoes, the yield of tomatoes. That's going to be the response. The growth of tomato, the yield of tomatoes is the response. But you know what? You are looking at effect of locations. How does location, has to, determine uh, the growth of tomatoes. Okay. But you know what? If there are other potential factors, okay, because if you want to study this alone, if you want to study this alone, look at what I circled. You're going to be thinking of analysis of variance. But you know what? If there's another potential factor, you know, that actually determine the growth of tomatoes, like temperatures, okay, and the hours of sunlight available to each tomato, then you're actually going to use analysis of covariance. In that situation, temperature and the hours of sunlight are covariate, though they are not of primary of interest, because what you actually want to investigate is to be able to see whether different locations, whether the tomatoes growth are the same in 20 locations. But you got in mind that their temperature also have effect, as and hours of sunlight also have effect. I could remember when I was in high school, in biology class, we did what we call photosynthesis. Photosynthesis. Okay. Has any one of you heard about photosynthesis in biology? Yeah. Photosynthesis is a process by which, green plant manufacture their food from carbon dioxide and using energy, absorb, so that is a process. So which means the sunlight, the hours of sunlight and the temperature actually uh is very, very important. Okay. Now in this example right now, you got two concomitant variables. Okay. So you got to use analysis of covariance here. Okay, so I'm actually going to move to another example. Uh, I walk you through this example on Monday, where we're looking at the effect of two categorical factors on the weight gain. And of course, we put into consideration the initial weight of the animal. Okay, the initial weight of the animal right here is the covariance that we're talking about, which is continuous in nature. And here uh, we got two factors, uh, a factor A and B that are categorical. If you don't consider the initial weight, you're actually going to end up using analysis of variance. And of course, because you got two categorical factors, you're actually going to use uh, two-way ANOVA with interaction or two-way ANOVA without interaction. You've done that before. Okay, what I'm trying to talk about right now, this guy here, if you only want to focus on that, if you don't want to focus on the covariance, what you're actually going to use at the end of the day will be two-way analysis of variance, whether two-way analysis of variance with interaction or without interaction. That's what you're going to use. But, and you know what? Using two-way analysis of variance here, you are only considering the final weight of the animals. Okay, I'm going to say that again. Using analysis of variance, you are only going to consider the final weight of the animals. Okay, but you know what? Using analysis of covariance right now, okay, because you are considering the initial weight of the animals before before they were given these factors. That is very, very important, because the initial weight of the animal could have relationship with the final weight. The final weight may depend on the initial weight, and that has to be put into consideration. When you are doing that, then you're going to use analysis of covariance. So why am I stressing that? I'm stressing that because um, you know just like the good news that's that came from FISA, we about the the vaccine for COVID-19. They've discovered a vaccine now that is that have more than 90% efficiency for the COVID. So which means, look at all this, why we have been trying to get, the vaccine, we are not able to get. And you know what? Uh, in science, this is allowed because we go from unknown to known. Okay, we go from unknown to known. Okay, it doesn't matter how long we are able to get something, but at the end of the day, we believe with science. When we pay more attention to science, we actually going to understand the world around us. Now, based on the example number 3 right here, this is the data that we're able to collect. Take a look at the data now. We got the initial weight. All the animals used in this research, we have a measure of their initial weight. Okay. And after that, uh, having the measures of their initial weight, then we get their weight uh, after they were subjected to, uh, after they were given uh, the, what is it called? The factor, the two factor that we talk about. We talk about the source of protein, and I'm going to show you now. Take a look at that, the levels of protein and the source of protein. Okay, so the data are available, and you know what? Based on this data right now, uh, this is a table. Take a look at the table. If you take a look at this table, you're actually going to see that we just executed the analysis of covariance. In the analysis of covariance, I said there's going to be covariance, right? And every other thing you're going to see is actually going to look like the two-way ANOVA you have done before. Take a look at this guy here. This is factor A, the levels of protein. This is factor B, the source of protein. This is their interaction. Okay. The only thing that is new in this table is this guy here, the covariance. And what is the covariance? The initial weight. That's what I wrote, initial. The initial weight. Okay. Now, uh, we've been able to obtain the table. Take a look at that. What is very, very important to me right now? Take a look at this guy here. That is the p-value associated with the covariance. To be able to justify the inclusion of the covariance into a model, that covariance has to be significant. Take a look at that. That is significant if you compare that to 0.05 level of significance. That is less. 0.00397 is less than 0.05. And because of that, the covariance is significant. And of course, you've justified including covariance in this model. Take a look at that. Okay. So, and of course, you can take decision regarding uh, the level, uh, the source, and the interaction. So take a look at that. That's exactly what we have. Okay. Now, uh, what are we trying to talk about? The dependent variable y, which is the weight of the animal here, is adjusted so that the covariate take on its average value for each case. Okay, we got to adjust that. Okay, and of course the effects of the factors A, B are determined using the adjusted value of the dependent variable. So I told you the concomitant variable has to be adjusted, which is the initial weight of the animal here, And it's after adjusting for that, after controlling for that, that you can actually take decision regarding uh, the factors. Okay. Now, like I said, the ANOVA and ANCOVA can be handled by multiple regression package by the use of dummy variable to handle the categorical independent variable. And of course, the result will be the same. I told you the other time, when we're dealing with the analysis of variance, uh, I show you the regression approach to that. So we got a package, and of course, I'm actually going to show you that how you can go about something like that. Now, uh, that is how that one is done. Now, in this example 4, I'm actually going to show you how you can actually run this in R. Okay, this example, I'm going to show you how you can do that in R. Of course, my TA will walk you through this in the next lab. But you know what? I'm actually going to show you now. Now, take a look at this question. I told you before, some of you, if you are having difficulty with data for your project, of course, it is not too late. I'm actually flexible uh, for practical 1 and 2, but without practical 1 and practical 2, you may not be able to, there's nothing you're going to do in practical 3 because you need your data, okay? And that is the reason why uh, maybe what we're doing right now will actually provide a clue, okay, to that. Now, take a look at example 4. Uh, you know, in an engineering company that is actually interested in, take a look at, they have 4 different formulations, okay, of an industrial glue, and they are being tested. And what is the response? The response is the tensile strength, okay? I don't know whether some of you, you've heard about Hooke's law in physics. Hooke's, that's what we call Hooke's law, okay? In physics, that's what we call Hooke's law. I talk about the extension in elastic the force, you know, uh, when the elastic material, is directly proportional to the applied force, stuff like that. Now, uh, here this company have 4 different formulations, and of course, they actually want to test whether the strength, the tensile strength are the same, the tensile stress of the glue are the same across formulations. Okay, and of course, uh, if you want to do that, you're going to use analysis of variance. But you know what? If there exists a covariate that have you know effects that also have effects on the response, covariate like thickness, thickness, thickness. You know, thickness also affect the strength. Okay, though that was not of primary of interest, but you need to be able to adjust that. Okay, now because of that, uh, you we have take a look at the formulation right here. We got formulation uh, from 1 to 4. We got 4 formulation. Okay, and you know what? Each formulation are being replicated. Okay, you know they are replicated 5 times, and of course, we replicate in research, in design, to have a measure of experimental error. Okay, now take a look at that. With each uh, was replicated 5 times, and that's what you can see. How many formulation do we have? We got 4 different formulation, and of course, uh, these are the corresponding strengths, which is the response. Okay, I'm going to call this is Y. Okay, this is Y, and the thickness is the covariate. I'm actually going to call that X. Okay, and the formulation is Z. Okay, because Z is the treatment. Okay, of course, you got 4 levels of the treatment, right? The 4 levels of categorical factor. Okay. Now, you are giving a data like this. How do you actually, what are you going to do? How will you run this in R? Okay. If you want to do this in R, uh, take a look at what I have here. This is a plot of the strength, that is the response, against the thickness at different formulation. Take a look at this. I'm actually gonna, my TA will walk you through how you can use the necessary code that will give you this. Okay, so this is the initial, uh, you know, this is the first thing you're gonna do. Trying to look at the, uh, in the preliminary investigation where you want to visualize formulation across the, uh, where I mean the strength across levels of formulation. There are four different kind of formulation right here. Okay, now this is the code. You know, even uh, so like I said, my TA is going to walk you through this. Now take a look at the code right here. Uh, that is the code, and of course, if you have that as a code, let me talk about this first one here. In the first one here, I'm only talking about uh, test of formulation differences. That is talking about test of formulation differences. We have four different formulation, and of course, we want to see whether the four different formulations are not and the same or not. But you know what? Take a look at this guy here. What is this? Model 1. What is this? Model 2. Now you remember, let me mark it. Model 1, model 2. What do you see in model 1? Model 1 is just when you're basically looking at the effect of thickness on strength. Why do I need to look at the effect of thickness on strength? I said, what I'm doing right now is a preliminary investigation that I need to be done. Before I can use analysis of covariance, because I need to be able to investigate, is there a relationship between the covariate and the response? That is what model 1 is talking about. In model 1, you're looking at the effect of thickness on strength, okay? Which means you actually want to investigate whether the covariates actually have, effects on the response, okay? Now, what are you doing in model 2? What you're doing in model 2, you are looking at the effects. It's like you are having a kind of multiple regression model where you are looking at the effect of two predictors. What is the first predictor? The first predictor is categorical, which is a formulation. Don't forget we have four different formulation right here. And of course, the thickness. Okay. Now, when you have model 1 and model 2, you remember that we're going to write the code is going to be ANOVA. You remember when you remember what we did in partial F test? What the partial F test, we actually want to compare between a simple model and a complicated model. Do you remember what we did before? The knowledge of that is required right here, because we need to be able, that's where we're going to start with. We're going to start from, okay? So now, model 1 and model 2, look at the p-value. In the non-hypothesis of this test, model 1 is appropriate. In the alternative, model 2 is appropriate. Now take a look at the p-value. What is p-value talking about? The p-value is 0.6405, and the p-value here is is greater than 0.05 level of significance. What are you going to do? You're going to fail to reject the non-hypothesis. And failing to reject the non-hypothesis, what are you talking about? Model 1 is good. What do you mean by model 1 is good? Model 1 is good means you have succeeded in justifying that the covariate has effect on the response. Because you need to first justify that the covariate, it is not all covariates that may have effect on the response. Okay? So how am I going to know? That's exactly what I'm trying to do right now. Trying to look at the uh, effect of the thickness. Okay, considering model with thickness and considering model with the formulation and thickness. And of course, you can see what we have. Now, what does this one, what are we trying to do right here? Now, take a look at that. We're also comparing two models. Okay, we're comparing two models. The first model, we're looking at the formulation. We're looking at the effect of formulation on strength. Don't forget that the formulation, therefore, is categorical. Okay, so we're looking at the effect of formulation on strength. And in another model, we are looking at the effect of thickness and formulation. Okay, and of course, for us to be able to justify the inclusion of the covariates into a model, we must reject the non-hypothesis here. Now, take a look at this. What is the non-hypothesis favoring? The non-hypothesis is trying to tell me use only formulation alone. And if you want to use only formulation alone, you are actually going to do analysis of variance. I'm going to say that again. Don't forget. I mean, we have 4 different forms of formulation. Okay. Now, what model 1 that I cycle right now is talking about is that conduct analysis of variance. And what is model 2 talking about here? The model 2 is saying, in an attempt to look at the effect of levels of formulation on strength, consider thickness, which is the covariate. That is what model 2 is talking about right here. I want you to take a look at that. And what happened? The non-hypothesis here is that, so which means, in other words, the non-hypothesis here is saying consider ANOVA. The non-hypothesis is saying consider ANOVA. You know, you are considering ANOVA when you are only focusing on the categorical predictor alone. Okay. Now, but what is the alternative telling you? Look at model 2. Alternative is telling you consider analysis of covariance. Okay. And that is why you have, look at that thickness. The difference between model 1 and model 2 here is thickness. In model 1, I'm not considering thickness, which means I'm not considering any covariates. And I'm actually going to use ANOVA in that situation. But take a look at model 2. What is it talking about? Model 2 say, consider thickness, which is a concomitant variable, as part of your analysis. And that will be analysis of covariance. Now, what is the result? You know, when I do the ANOVA of that, look at the p-value associated with that. Oh my God. The p-value associated with that is less than any reasonable level of significance. What am I going to reject? I'm going to reject the non-hypothesis. When I reject the non-hypothesis, it means I'm rejecting ANOVA. What am I going to consider? I'm going to consider analysis of covariance. Did you see that now? So what we're doing right now is part of the preliminary investigation. Okay? Because we don't just go ahead to use a model. Then we need to investigate whether, you know, assumptions underlying the use of model holds. And the reason why we don't get things right in the world at times, we don't really consider assumption. And we got to consider assumption because all statistical models have assumptions. So right now we've justified, you know, inclusion of the covariate. Now, after that, then we can go ahead, you know, to do whatever we want to do. Now, take a look at this right now. We are now considering full model. Okay, what is a full model? The model that have the formulation and the thickness. Okay, therefore the summary of the model, you know, we need to get a summary of the model, and this is the summary of the model right now. Take a look at that, where you were able to you know, consider, if you take a look at this summary right now, you're going to see thickness, okay, along with the formulations, okay, and of course you can take decision regarding each of the formulation, okay. And I think I need you guys to ask a question now. Can somebody tell me, I have 4 formulation. Why is it that formulation 1 is missing for extra credits? Why is it that formulation 1 is missing in this output? That's why they try to have 4 formulations. Can somebody tell me?
Because
Okay, you guys
formulation
see
one
anything?
is
Okay,
zero.
go ahead. Okay, go ahead. Go
Because
ahead.
we need one formulation to be zero.
Because we need one formulation to be 0, so which means we're going to make it as point of reference, right?
Yes.
Thank you. You said a message to me for extra credits. You know, when you have k number of categories, you're going to consider the dummy. And what is the dummy? Here is actually going to be the number of categories minus 1. Okay. If you have 4 formulation, 3 formulation will appear in your table. And that's why you are seeing that right now. Thank you. Okay. Now, uh, this is the full model, and this is the reduced model. Of course, in the reduced model, we only consider thickness, the covariance. In the full model, we are considering the combination of the two. Okay. And of course, that will enable you to take your decision. Okay. Now, look at this is a plot. The strength against the thickness, a different formulation. Okay. And how many lines do we have? We're going to have 4 lines because we have 4 formulation. Okay. And you know what? You remember I showed you an assumption the other time where the lines should be parallel. We expect the line to be parallel. Look at that. They don't intersect. Look at that. This is trying to tell us that what we're doing is fine. Look at the line. They are parallel. They are expected to be parallel. A different formulation, you know, the scatter diagram between the strength and the thickness have to be, you should have a parallel lines, a different formulation. Take a look at that. Okay. Now, uh, you can also check for the absorption around the thickness. You remember, of course, this we're doing linear regression now, and of course, you remember the absorption of linearity, normality that we have done before. Okay, have to come into play. Okay, now, lastly for today, you remember that yesterday on Monday I was talking about auditing example. Okay, where I said a particular accounting firm, they want to study the effectiveness of 3 different methods of training statistical auditors. Of course, this research was carried out by Kotner and et al. 2005. Okay, and of course they have 3 kind of methods. Method A, study at home with provided materials. Method B, train in local offices with local staff. And method C, train in Chicago office with national staff. Okay, now you remember I said um, what they actually want to measure here, what we want to compare here is the proficiency in auditing. Okay, of course, if you want to just do this, you're going to use analysis of variance. But you know what? We also need to consider the initial, the initial, uh, we need to have the measures of the auditing of the proficiency before the training. Okay, because of that, 30 auditors were blocked. Okay, into 3 groups. We assigned 10 of them into these 3 groups, which are randomly. Okay, so and before they were assigned to the group, we actually have a measure of their proficiency. Uh, we measure their proficiency level in auditing. Okay, and that's going to be the pre, the one I call the pre right here. Okay, so which is more or less like the initial values for the proficiency that we talk about. Okay, now take a look at this. This is the code. For across different method, uh, we have the the measurement for their proficiency in auditing before the test, and this is after for the training, and that is after the test. Okay, take a look at that. We have a lot of data here. Now, this is the hierarchy code. Okay, take a look at that. But you know what? What is the first thing we need to do? Before fitting an ANCOVA, you need to check if there's a relationship between X and Y. You need to check if there's a relationship between the response and the concomitant variable. We also need to say if the parallel slopes, if they are parallel slopes, okay? And we also need to test if the covariate X and the treatment Z are related, because we don't expect the covariate and the treatment to be related at all, okay? And we also need to test whether the assumptions of homogeneity or variance hold, okay? Now, take a look at this. What am I doing right now? I'm trying to, if I want to study, one of the assumption, is there a relationship between S and Y? Is there a relationship between the covariate and the response? Look at that. This is the code. We've done that before. Looking at the effect of pre on post. Okay. The proficiency level how does the initial proficiency level of the auditors affect the post? Okay, that's exactly what we're doing right now. You did the ANOVA for that. Oh my God, what does it tell us? That is telling us that is significant. It means the covariate here is significant. What is the covariate? Okay, the initial proficiency level of the auditor before training is the significant here. Can you see that now? Three. So which means it's related to the post. Okay, this is the initial thing we're going to do. Now the assumption underline that old. There must be relationship between the response and the concomitant variable. That's exactly what I'm showing you right now. What is the next thing you're going to do? You're going to test for parallel slopes. I told you, the slopes have to be parallel. This is the code. Now take a look at that. Oh my God. How do we test for parallelism? You're going to use two-way ANOVA with interaction. Take a look at this. This is what I want. This is interaction. Prayer method. What is a pray? Interaction between what? Interaction between the concomitant variable and treatment. Don't forget the treatment is method. What happened here? What is the p-value? It's not significant. What do we expect? We don't expect relationship between uh, the treatment and the covariance. And that's exactly what we're seeing right here. Okay? Now, this assumption also hold. Can you see that now? Then the next assumption that we want to investigate is there a relationship between covariance and treatment? Okay? Uh, and of course, uh, give me 1 second. Yeah, you look at the interaction right here. Now, the uh, the relationship between the covariance and method, rather, talking about method. And of course, we don't also expect relationship. Take a look at that. Look at this guy here. Okay. You know, right now we're looking at the effect of method on the pre. Okay. And it is not significant. And that's expected, right? Okay. Now, what about the homogeneity of variance? Okay. We want to use Leibniz test for the homogeneity of variance. And this is what we have because the non-hypothesis will actually tell us the variance are the same. Alternative is going to tell us the variance are not the same. Look at the p-value right here. The p-value is greater than 0.05, and which indicates the variance are the same. Now, all the assumption hold for this data. Then if the assumption hold, then you can now proceed to the ANCOVA table, okay, where you are looking at the effect of method on the post, okay? So look at that. Now you can take your decision regarding the method, okay? It means different levels of method have different, the proficiency level are statistically different. Okay, that is what the p-value is actually telling us here. But you don't go to that without first investigating assumption. Okay, then from there we do multiple comparison tests, also in analysis of covariance. Why? Because take a look at this. The non-hypothesis is rejected. We got no choice. We're going to do multiple comparison tests to know where the difference lies. Of course, take a look at this. It made the difference actually lie between those two methods. Okay, take a look at that. Okay, then that is interpretation. Then you go to fitting on centered ANCOVA. Okay, get your results. It's significant. You can see that now. Okay, you have the interpretation, and that is how far I can go today. On Friday, I'm actually going to go into what we call contrast in experimental design. Is there anyone who want to ask question before I go away today? Is there anyone? What is the purpose of the summary mode? Yeah, the summary mode, when you run a model, the summary mode is just to give you an output, your results. Okay, let me go back. Where if you're referring to I don't know the one you were referring to, but if you're referring to this guy here, of course, we're always going to have a summary of that. Okay, to have the results. Okay, so I don't know whether I've answered your question. Like I said, my TA is going to walk you through this in the lab. But before the lab, you can be trying to run this code yourself. And of course, uh, that is that. Is there anyone who want to ask question before I go today? Is there anyone? Okay, like I said on Friday, I'm gonna walk you through another exciting topic or contrast in experimental design. In case if there is anyone who want to or who need clarification, please meet with me during my office hour. You pay for this service, you deserve to be served better. Okay, you pay for the service. Please do not hide your feeling. Problem disclosed is problem solved. Okay, I want to appreciate everyone who have attended my lecture today. I hope you guys enjoy my lecture. Until on Friday that I'm going to call your way again. Please stay safe and have a good day. Bye for now, guys.
You too. Thank you.
You're welcome. You're welcome.